Okay, how to define a flexible nozzle in CSiPlant. Let's draw in some pipe, going to a nozzle location. This will be where we draw in a flange. Pick the flange icon, pick the incoming side, the eye side of the flange. We're going to connect to the endpoint, the flange face there. Okay, now let's define these sections for the nozzle and the vessel. We'll make one called nos. Now that's going to be NPS 14 shed 80. We'll assume it's a carbon steel A106 or equivalent. Now let's add one for vessel. Now the vessel will be a 2000 mil OD with a 20 mil wool and a carbon steel as well. Now we also have to make those quickly into pipe properties sets, but that's very easy. Just make one called nozzle and add the nozzle section. Apply, and then one for the vessel. Now to draw in the nozzle. Just note that CSI will introduce a reducer even if you don't have a change in diameter. I'm going to change that reducer length to only 3 mil, so it's more like a gasket. Change over to the nozzle property set, draw in the nozzle. This takes us to the intersection with the shell. This is going to be a hillside nozzle. From here I'll change over to the draw point tool and put in the offset to the center line of the vessel. This will be a 1 meter radius with a 45-degree angle. Okay, change back to draw pipe. Let's get rid of auto add elbow. Draw in the branch into the center. Now we want to change over to the vessel section, draw down to the base. You'll see it looks a little bit odd. What we actually want to create is a T, so let's actually change to the line view so we can see what we're doing a bit better. Zoom in on that and draw a T. Let's zoom out a little bit. We can see our T here. Let's click on that. Right click to show properties. You'll see the branch length there. That's actually modelled as rigid by CSiPlant. Let's change it so that it goes right up to the ID of the vessel. Now let's zoom in on the wall section. What we actually want to do is to divide that up and take out a small chunk. We're going to have a flexible anchor bridging that gap. So we use the divide pipe feature. That's also available from the edit menu. Okay, I'll also divide it again. Sometimes it can be useful to have an extra division in case you want to define SIFs on the outgoing pipe. This is the little section we're going to delete. Just hit delete. Now let's choose draw anchor. We'll draw an anchor on the vessel side of the connection. It's a bit funny the way it draws it off to the right like that. It really should be closer to the joint of interest. Hopefully that will be improved in future. Now we'll need to select the joint on the pipe side, select the anchor itself, and we'll go to assign pipe support connection. We need to join these 2 points up, join by point ID, the selected point, apply, and it fills in that gap. Now it does actually look like pipe, but you can see for yourself that it's not by turning off the supports like this. Let's turn that back on and show the support number. Let's also have a look at the joint numbers. You can see it's going from A to C here, meaning there's a change in pipeline definition across that gap, which makes sense. Now we actually want to right click on the support and change the support definition into a flexible anchor. So we'll take a copy of the existing anchor, give it a new name, and we'll fill in the stiffnesses from our FEA plugin. So U1 being the radial direction, Then we'll have U2 and U3 being shear directions. We'll normally leave those rigid. R1 torsional is pretty rigid. Let's move to R2, the circumferential direction. Give that a stiffness. Newton millimeters. Let's change that to meters. It's pretty odd the way it shows joules, which dimensionally is the same as Newton meters. So let's put that one in. Newton meters per radian, and R3 being the longitudinal direction. Okay, check that it's transferred across. Yep. Okay, let's check the local support axes. This is how we check to see if we've got things defined correctly. Just hide flow arrows, which confuses things. So the axes are shown red, green, blue, which is the order 1, 2, 3. So try and get used to that order: red, green, blue, radial stiffness, circumferential bending stiffness, longitudinal bending stiffness for this nozzle. Now let's quickly put in that flange that we didn't put in before. We'll go to the J side of the joint, starting from the start point. We'll just go the other side of this 3mm gasket section. Ignore that warning. Okay, let's zoom out a little bit, take a look at the model, hide our local axes, have a look at 3D view. Let's add an anchor to the base of the vessel, and then one to the start of the pipe. Another good thing is to exclude the T from the code stress checks, which we can do by creating a group. So we'll go select, we'll invert the selection, then we'll add the rest of the model to a new group. So we'll define a group, add to the group, then we'll want to go to design requests, and we'll tell it to look at only that group for the code stress checks. Design group. You can select that to see what it looks like. Okay. Maybe we'll want to also assign a temperature, any other loads, temperatures and pressures. Reset the view. Okay, so let's analyze that. Once we've analysed it, we'll just take a quick look at the displaced shape, just to show you that the displaced shape behaves as expected. We need to pick our gravity and pressure case. We'll show the UZ direction on the contours. Let's change to the line view. You can see there that the T is staying horizontal all the way across. The Z displacement is 0, which shows that it's rigid in there. Then after that, it turns downwards. Now let's take a look at the operating case, gravity plus temperature and pressure. Let's take a look at one of the horizontal directions on the contours. We'll move to a view from above. Now let's zoom in on the nozzle. Let's try and find our flexible nozzle. Let's zoom in just a bit more, and there we see clearly the difference in displacement at those 2 points, and we can see by hovering over each one of them the difference in displacements and rotations. So the flexible nozzle is behaving as expected.